All right, everyone, continuing on, we're going to have conjugate additions. And conjugate addition means that we have a conjugated system, and that's going to act as our electrophile in this case. So nucleophile will come in, and there's multiple places where we might choose to attack. So for example, here's an example of our enolate that we had from last time. So that's our nucleophile. And this nucleophile has two options for attack of an alpha-beta unsaturated system. Now remember, these came from things like our Aldol condensation reaction, so we're going to make a connection to something we learned before. But the conjugation is right here, so that's a conjugate system. And what we have are two possible sites for reaction. Through just previous knowledge, we know carbonyl oxygen, that this carbon here is partially positive, so the nucleophile could come and attack there. But we also know through resonance, where you can picture, that these electrons can flow up to there, that makes this carbon here also partial positive. So resonance structure, I'll show you. So in the resonance structure, you can see how with the electrons flowing like that, we can have a positive charge character on this beta carbon. All right. So with that in mind, you might wonder, how do we get the nucleophile to attack here instead of here, or vice versa? How do we control where it attacks? Well, it turns out that certain nucleophiles just prefer attacking at the 1,4 position, and some attack the 1,2 position. And when I say 1,4 and 1,2, if you recall maybe from last quarter, we have a funny way of numbering that. We could either have a 1,2, there's a conjugate, there's a pi system there, and then we have a 3,4, we have the pi bond there. So we have addition either where this will attack 2 or this will attack 4. So we call it a 1,2, 1,4, addition. So for 1,4 addition, these are the lists of nucleophiles, and these are the lists of electrophiles that pair together to do a 1,4 conjugate addition. And we call this conjugate addition a Michael reaction or a Michael addition. So we have Michael donors, which are our nucleophiles, and the Michael acceptors, which are electrophilic. And notice for all the Michael acceptors that we're talking about these carbonyl systems, that we have alpha beta unsaturated carbonyl of some kind. Now whether it's an aldehyde, ketone, ester, amide, even cyanide, remember that's a derivative of a carboxylic acid. So that can come from, or carboxylic acid can come from here. So, or nitro group even. Okay, these are electron withdrawing groups here, and these can help pull these electrons over toward itself and make that beta carbon more positively charged for attack. These are what we call soft electrophiles, because we're talking about the orbitals on carbon, which are larger than the orbitals on oxygen. Oxygen's a smaller atom than carbon. So we sort of call it soft. When things are maybe large, orbitals are larger, sort of more spread out, diffuse, or fluffy is another word I heard for that. Okay, well, likewise, nucleophiles that are also sort of spread out, diffuse, and soft are ones like enolates with between two carbonyls, not just any enolate, because remember, an enolate is just one carbonyl, so there is some resonance, but if you can have two carbonyls, that makes it even softer. So these tend to react more at the 1,4 position than even just one carbonyl. Okay, so this is what we call a soft nucleophile as well. So notice the pattern here. But in addition to that, we also see that this will help pull the electrons through. So there's more resonance delocalization here. So this is considered soft as well as the lithium cuprate, which is the Gilman reagent. And so that's in contrast to the Grignard reagent, which is a very hard nucleophile. Gilman reagent, because copper is bigger, might promote for softer orbitals. Okay, we are going to practice our Michael reaction. So notice that we're going to use one of these and one of these. So let's figure out a mechanism for this reaction, and just keep in mind when we're going to make an enolate in the first step, we're going to attack and do 1,4 addition, and then we're somehow going to use acid to get the carbonyl back. So let's see how this works. In our first step, we're going to deprotonate an alpha. In our first step, we're going to use a strong base, and it doesn't really matter if it's hydroxide, ethoxide, or methoxide. We tend to use hydroxide if it's just for a ketone or aldehyde. So here we have this compound, and then we're going to use this as our nucleophile, and this will be our electrophile. So our nucleophile, remember, this is a kind of Michael donor, and this is a kind of Michael acceptor. So in this reaction, this is going to attack at the 1,4 because it's considered a soft nucleophile. And we'll do this kind of electron pushing here. After that step then, we end up with a new bond right here. And then here's the methyl group of the Michael. Here's the pi bond that moved. So I'm sort of counting it 1, 2, 3, 4. Here's 4. 3 got attacked. 2 and 1 have a new pi bond now. And then we release that to the oxygen. So this is my new enolate ion after attack. So we're adding these two together. So this is a Michael addition, or sometimes we just call it reaction. All right, so now compare this to this, and you'll notice that the only thing that's different is the part right here. Do you guys know what's going on there? Enolate to a keto. Okay, so the enol keto tautomerization is going to happen here. Can you guys show me when this gets protonated by acid in the next step, how do I end up with a ketone? Okay, go ahead and pause it and see if you can put an H on here, make that neutral. You have an enol. Okay, we could do that part together if you want. This will grab H plus and we'll have an enol. So then show me what that enol looks like, and show me how in acid that can be catalyzed to a keto form, which gives us our final product. All right, guys, how it works is you just bring these oxygen lone pairs down, and then we use the pi bond to grab an H plus. Now that's sort of confusing. Does that mean the H plus is here or here? So I like to just sort of, something I learned from Andre Stramanis is to bounce the electrons to here and then attack here. That way you know what's happening, but sort of like that enolate is sort of forming again, or the electron charge is moving in this direction, so it's putting negative charge on this alpha carbon. And that's how you get the keto form. All right, the major product of the 3 following steps, so following the same thing, you'll be able to show the Michael product there. Again, I know it's going to be a Michael reaction because I have this alpha enolate that's between 2 carbonyls, and I see a conjugated reactant here. So I know there could be a chance that I'm going to attack here, not the carbonyl. So go ahead and give that a try and show me what you get. Now, some of you are going to have a hard time sort of drawing these out at first. So my tip is just take this molecule and transfer it over here. So I always start, like even with aldol, claisen, I would just start with that molecule and just anchor it. And then I draw like what we're adding to it next. And I use mechanism and arrows to figure out what that's going to be. Like I know this is going to be conjugate addition. So what I'm going to do is make sure that I draw a new bond from that alpha carbon to this end point carbon. So here's my new bond. And from then I just sort of trace it back. And if you need to number, that's totally fine. I just sort of number it so I know there's a 3rd carbon that I just drew. And then I have carbon 2. And then I have carbon 1. And then I have the carbonyl. So just do a little bit at a time and go back and make sure you didn't add any carbons or added the right number of them. And then just make sure you know where your double bond ends up. Okay, so it never hurts just to go back and say, okay, 1, 2, 3 off the cyclohexyl group, 1, 2, 3 carbons off the cyclohexyl group. Now at that point, remember this gets neutralized and then we have the tautomerization. So then I won't see a pi bond here. So my final product is going to be this one here. So note that the Michael donor is not just any enolate. It's got to be softer so that it can be compatible with the 1,4 addition. So you really, if you see something like this, it's more likely that it's going to attack at the carbonyl carbon. So just be aware that you might get more competition, with a regular enolate where it might attack at the carbonyl carbon otherwise. Okay, so that we really need to look for these special Michael donors to know. So in order, though, to make, let's say that this is all we have, is there a way I can modify it to make it softer to become a Michael donor? So it turns out that there is a way you can. In fact, an enamine is a soft nucleophile. So if I can make this into an enamine, and we learned this in chapter 19 with this first step, we use a secondary amine in a little bit of acid to catalyze the reaction, we can end up with an enamine. Can you guys tell me what is the enamine of this ketone? So it's sort of a lot of steps, but maybe you remember from the ketone aldehyde chapter, the first chapter we did this quarter. You grab some acid here, you activate the carbonyl, the base comes in, or you may or may not activate this carbonyl, but it's there to neutralize things and proton transfer is needed. So here we have this, and then we want to deprotonate here and protonate here to lose that water. And then we have the imine that gets neutralized to the enamine. Okay, so that's all step one, and that's from before. So now that we have this enamine, this is what we consider our soft nucleophile. So once we have this enamine, it becomes a soft nucleophile, and the lone pair will come down. We'll have this negative charge on the alpha carbon, and then we'll attack the 1,4. So let's show that in the next step. All right, so it looks sort of messy, but here this lone pair on the N will come down. We'll make a double bond here. And we will alpha alkylate at the 1,4 position for this Michael acceptor. And what we'll end up with, let's draw it out. All right, so then now we have this intermediate here after the attack, alpha attack there. So then we have our last step, which is acid hydrolysis. What happens here is two things. One, this gets neutralized into its keto form, just like we did above. Right here, this last step right here in the previous page. So we have the enol keto tautomerization. And then we also have hydrolysis of the imine that results back into the carbonyl. And how that happens is through the reverse of all these steps. If we had water, we would get the water attacking here, releasing this, getting protonated, eventually turning this into a leaving group. All right, and so the next thing to look at is that if we tried to do a different way of alkylating, we would not get the best results. We really get the best results with this reaction going through an enamine if we just have one carbonyl. So the point of this is that with the one carbonyl here, this is considered an enolate over here would be considered a hard nucleophile. So this here, LDA would grab here, we'd have just one carbonyl. That would be a hard nucleophile. And so it would rather attack here at the 1,2 position. So in order to avoid that, we went through the enamine, which is a soft nucleophile. And this softer nucleophile is what's going to promote 1,4 conjugate addition. And so this is the 1, 2, 3, 4. You could see the new bond at the 4th carbon here, or the 4th position, as opposed to here, if you tried to do this with LDA, instead of going through the enamine, which is soft, you have this. This is considered a hard nucleophile. It's not going to really necessarily get directed toward that 1,4 addition, maybe 1,2 addition instead. So if you try to go for 1,4, then this would not be an ideal method. Therefore, if you have one carbonyl, it's best to go with an Stork enamine reaction, which is this one. Let's add this to your list of reactions for this section. So you had malonic ester, you had acetoacetic ester, and now you have the Michael and you have the Stork enamine. Okay, so that's 4 reactions so far. So let's do an example of how to apply the storic-enamine reaction. First, I notice I can make an enolate here, but if I'm trying to do a conjugate addition, and how do I know I'm doing a conjugate addition? I'm looking at this molecule I have, and it sort of means that the rest of this needs to get added on. I know there's lots of ways of adding R groups, but the reason why I know it's going to be a Michael type addition is because I have a 1,4 conjugate addition. I can just see that 1, 2, 3, 4. I'm adding to the beta carbon of this conjugate system, or should be conjugated when I start off. So I know it's going to be Michael addition. So if I know this is a hard nucleophile, I need to soften it up. I'm going to use the storic-enamine. So my first step is to make the enamine out of this carbonyl by adding some kind of, and it doesn't matter what it is because it comes on and then it comes off, right? So I just need any kind of amine. So maybe I'll just use dimethylamine and some catalytic acid just to help aid in some of these proton transfers. All right, so once I have that, then I can identify my Michael acceptor is going to be that a carbonyl containing compound that adds these carbons on. So it's got to look like this molecule. Now, one mistake you might make is you might just draw this and say that's good. But remember, this is not reactive unless I have something on here that makes it reactive. So this by itself is not great. I want it to add to this carbon. I need to make this carbon reactive. And to do that, I'm going to add a pi bond here. So now it looks like a Michael acceptor. And it's a conjugate system. And it's going to want to attack here. So then the electrons flow this way, and then I do the tautomerization, and I get my carbonyl back. But I need to do one more thing for that to happen, which is I need an acid workup. So this is our storic-enamine reaction. So please go ahead and try these when you get a chance. And we're going to look at one more reaction, which is a combination of a Michael addition with an aldol reaction. It's a Michael addition and a Aldol condensation. And the name of this reaction is called Robinson Annulation. It's named after Sir Robinson in England. And basically put these two reactions together to do an annulation, which is a word for cyclization, to make rings. So let's see if we can figure this out step by step. Notice that our first step is a Michael addition. So what might we do in a Michael addition? We've got sodium hydroxide, so we're going to use that to make our enolate. And notice that our alpha hydrogens are here, and here, and here, but the most acidic one is here because it's resonance stabilized by 2 carbonyl groups in its conjugate base. All right, so once we have that, I'm going to attack the enolate at the 1,4 to do a 1,4 addition on this Michael acceptor, and let's show what we get then. All right, so after this attack, we have 1, 2, 3, 4 carbon chain, 1, 2, 3, 4 carbon chain with the enolate ion. Now at this stage, I can bring this back down, and we know that we have some source of proton in solution, like from water. So whenever sodium hydroxide, you see that it's usually aqueous sodium hydroxide, unless stated otherwise, might be dissolved in something like alcohol instead or something else. But in our case, aqueous sodium hydroxide. So once we have that, then we're going to have the keto form, and then we do an aldol condensation, but this reacts with itself in the aldol. So take a look here. Our product is to cyclize this, so I need a new bond between this and this. And so if I had this become an enolate, it'll attack here, and I'll have a beta hydroxy group. This will be hydroxy right here. And then I'll do the heat, and I'll get the condensation. So let's show the mechanism for that. So now here's my initial aldol addition right here to get my beta hydroxy. And notice I don't have that really acidic hydrogen anymore. So that's really nice to have an extra methyl group to avoid getting an enolate here and closing it up this way. Okay, so we're going to grab this this alpha hydrogen because this one can cyclize into a more stable 6-membered ring. All right, but can it form an enolate here and this can close up? It's possible, but if this closes up here, it's a 1, 2, 3, 4-membered ring, which is not so stable. So this enolate may form, but it's not going to cyclize. Could it cyclize over here though? 1, 2, 3, 4. So again, a 4-membered ring this way. But it brings up a good point that you have multiple possibilities because you've got all these carbonyls. You have to evaluate all the different alpha hydrogens and what the possible attacks are. So you will need to know eventually maybe an explanation for several possible products that could occur. All right, so in this reaction then we have finally the last step, which is the condensation. So I'm going to show that here. So first we deprotonate with the base to get our enolate here. And then the technical way of doing this mechanism is once we get that enolate, we use that to attack and release there. So that's how we get that double bond eventually. I'll just sort of show it in one step though. We have that basically. Okay. So that will lead to our Robinson annulation product. And let's notice that what do we accomplish here? First, we alpha alkylated. So we added this group here as our first step. And then our second step was we closed the ring. And then the third step, and that was with an aldol reaction. And the third part was to do that condensation. So that means that when we think about working backwards, you might want to consider that there was a bond forming right here. So we might need to think about this adding on here. And there also was a bond forming here from this aldol reaction. So this is how we figure out what our reactants are. Is we needed this piece and we needed this piece to annulate together. So when we work backwards, maybe analyze this and figure out what are the reagents you would need to do a Robinson annulation. So again, what I did was I needed an alpha enolate, so it probably was here that it added on. And so I had one group add on here, and then I had also, okay, so that is sort of analogous to this first one. And so this is probably the alpha beta unsaturated carbonyl the Michael acceptor that I used. So maybe this was conjugated right here. And then I did an alpha enolate here, attacking here. So maybe this right here was my next bond. So my reagents are going to be some kind of aldehyde. And let's do it upside down just so that you can match it up with what we got. So probably had methyl group there, that's this one. And then here, there was some reason why this attacked here. There must have been a carbonyl there. Okay, so there's my carbonyl. So that's probably what I started with, was this. And then I ended up adding to it this Michael group, or acceptor, which was the rest of it, which is this. But again, to make it react here, I need to add a pi bond there. So enolate here, reacted here, then this came here and attacked that. This became a beta hydroxy group that then did a condensation to make a pi bond there. All right, so this plus this, and then what else do we have? We have NaOH, and that's our Robinson annulation. So if you see a cyclic product, that should be a signal that you're doing a Robinson annulation. You need two pieces of that. Think of Michael and aldol.